Have you ever really stopped to think about how a computer, well, computes? How is it possible that a bunch of tiny on-off switches, literally millions of them, can work together to do complex math or make decisions? Well, today we're going to pull back the curtain on all of that. We're going to deconstruct a computer's brain, piece by piece, to see exactly how it all works. All right, let's jump in. Whoa, okay, this looks pretty complex, right? And, it is. This is an Arithmetic and Logic Unit, or ALU, built by a student named Lalo Morales for a lab project. This is the part of a computer that does the actual thinking, the heavy lifting. But instead of getting overwhelmed, we're going to use this as our roadmap. We're going to take it apart, look at every single building block, and then put it all back together. By the end, you'll know exactly what's going on in there. Okay, so before we can even touch the circuits, we have to learn the language they speak. And honestly, it's an incredibly simple language. It's made up of just two characters, 0 and 1.
And that language is called binary. We're all used to our decimal system with 10 digits, 0 through 9. Well, binary just has 2. You can think of a 0 as off and a 1 is on. It's the most basic, fundamental way to represent information with electricity, and it is the foundation for absolutely everything that's coming next.
So, how does this actually work when you're counting? It's really the same logic we use every day. In our system, when we count to 9, we run out of digits, right? So we add a new column to the left and start over at 0, making 10. Binary does the exact same thing, just way sooner. So the number 1 is 1, but for 2, we're already out of digits. So we add a new column and write 1, 0. 3 is 1, 1. And for 4, guess what? We're out of digits again, so we add another column and get 100. See? Same principle, just fewer symbols to work with.
Okay, so we can write down numbers. Big deal, right? The real question is, how do we get a circuit, just a bunch of wires and switches, to actually do something with them? Like addition. How can we make it add 1 plus 1 and get 2?
Well, meet our first building block, the full adder. This little circuit is an absolute work of genius. It takes in 3 single bits, we'll call them A, B, and a carry-in bit from a previous step, and it spits out 2 bits, a sum and a carry-out. Just look at that truth table. If you add 1 plus 1, the sum bit is 0, but the carry bit flips to 1. Put them together and you get 10, which is 2 in binary. It works! And this, right here, is maybe the most powerful idea in all of digital design, modularity. We don't have to start from scratch every single time. Once we've built and tested a simple, reliable component like this full adder, we can basically treat it like a single black box. It's a proven subcircuit that we can now use to build much, much bigger things.
And this slide shows that idea perfectly. See those 4 boxes labeled full adder? We've literally just daisy-chained 4 of our basic blocks together. The carry-out from the first adder becomes the carry-in for the second feeds the third, and so on. And just like that, we've gone from adding single bits to being able to add 2 4-bit numbers. We've built a more powerful machine just by combining simpler parts.
All right, so our circuits can do math. Awesome. But that's only half the story, isn't it? A computer also needs to make choices. It needs to select one piece of data over another, or choose which operation to perform. How on earth can a simple circuit do that?
Say hello to our next key component, the multiplexer, or MUX for short. And I love this analogy of a railroad switch. It's perfect. It has 2 data inputs, A and B, and then a single control line called S for select. If that select line is set to 0, the data from input A gets sent to the output. But if we flip it to a 1, the data from B gets to go through instead. It's basically a traffic cop for data. And hey, what do you know? It's our old friend, the sub-circuit principle. We can take 4 of those simple 1-bit muxes, wire them up together, and now we have a 4-bit mux that can choose between 2 entire 4-bit numbers. This idea of building bigger things from smaller, proven blocks, it's everywhere in digital logic.
I had to share this quote from the student's lab report. After he got his multiplexer circuit hooked up to some digital displays, he wrote this. It just perfectly captures that aha moment, That feeling when the abstract diagrams on a screen suddenly connect to something real and familiar. It's when the theory finally clicks, and man, that is a great feeling. Okay, so our circuits can do math, and they can make choices, but now we come to the next big question. What about memory? This is a huge leap. How can a circuit, which just reacts to whatever's coming in, actually hold on to a value? How can it remember a 0 or a 1 even after we've taken the input away?
So to figure that out, we have to understand this really fundamental split in circuit design. Everything we've seen so far, the adders, the muxes, that's all called combinational logic. The output is a direct, immediate result of whatever the inputs are right now. But for memory, we need something called sequential logic, where the output depends not just on the current inputs, but also on what state the circuit was in a moment ago.
So what's the trick? What's the magic ingredient that lets a circuit remember its past? It's a concept that's both beautifully simple and incredibly powerful: the feedback loop. We are literally going to take the output of a circuit and feed it right back into its own input.
And this slide just shows it perfectly. The difference one tiny change can make is amazing. On the left, if you feed the output of a single inverter back into itself, you just get chaos. It oscillates like crazy, totally useless. But look at the right. If you link two inverters together in a loop, you create a stable circuit. If the output is a 1, it loops around and reinforces itself, keeping it a 1. If it's a 0, it loops around and keeps it a 0. It will hold that value forever. And boom, just like that, we've created a memory cell.
Now, obviously, a memory cell you can't ever change isn't super useful. So the final piece of this puzzle is to add some logic gates into that feedback loop. This gives us control. It gives us inputs that let us set the memory to a 1 or reset it back to a 0. And this controllable memory cell is called a latch, and it's the fundamental piece of all computer memory.
Okay, deep breath. We've deconstructed the key components. We know how to do math with adders, we know how to make choices with multiplexers, and we even know how circuits can remember things using latches. So, it's time. Let's put all the pieces back together and take another look at our ALU.
And here we are, right back where we started. But this time it shouldn't look so intimidating, right? It's not a mystery anymore. We can actually look inside and recognize those blocks. We can see the adders for doing math. We can see the multiplexers being used to choose an operation. It's a complex system for sure, but we now know it's built from simple, understandable parts.
Here's one more great insight from the student's notes. While troubleshooting, he realized he'd made a tiny mistake. He'd defined his main inputs as being only 1 bit wide when they needed to be 4 bits. It's a perfect real-world example of how these systems are layered. A bug in the top-level design was actually caused by a setting in the sub-circuits. Everything has to work together from the smallest piece to the entire system.
So what's the end result of all this work? What can our little machine actually do? Well, it's incredibly versatile. Just by flipping a few control switches, this one circuit can perform a logical AND, it can add numbers, it can subtract, it can negate a number, or it can just let a value pass straight through, untouched. All of that power, all of that flexibility, born from just a handful of simple building blocks.
And that just brings us to this one final really big thought. We started with the simplest possible thing, a switch that's either on or off, a 1 or a 0. And from there, we've built layer upon layer of complexity, creating arithmetic, decision-making, even memory. It really makes you wonder, if all of this is possible starting with just on and off, what are the real limits? Is there anything that can't eventually be built with logic? That's a question that drives the whole field of computer science.